So we had just come up with the following conclusions for this enzymatic scheme. You have a rate of enzyme substrate binding to make the enzyme substrate complex. Then you have irreversible rate determining step whereby the enzyme substrate complex is converted to the enzyme product complex, and then you have fast dissociation to regenerate your enzyme and liberate the product. And based on the steady state approximation, we came up with the following equation for the following rate law for the rate of product appearance that depends on the total enzyme concentration, the substrate concentration throughout the reaction, and that substrate concentration appears both in the numerator and the denominator. And then we have this Km, this Michaelis constant, which is kind of weird because it equals K minus 1 plus K cat divided by K1. And we said that for this process, enzyme substrate binding, the Kd for enzyme substrate binding would be equal to K minus 1 divided by K1. So even though some people, we talked about last time, like to think about the Km in terms of like substrate binding, how tightly it binds to the enzyme, it doesn't exactly mean that. It only means that if Kcat is really, really slow, in which case that's a terrible enzyme. So interpreting it can be a little bit difficult. But we want to talk a little bit about how you expect the rate to depend on these various concentrations. For example, notice that the rate is first order in enzymes, so increasing enzyme concentration should increase the rate linearly. For substrate, it's a little bit different. Okay, so what do you predict when substrate concentration is low? What do you predict in terms of the dependence on substrate concentration? By that we mean low less than Km. What would the rate law simplify to? Kcat, enzyme, substrate, and then maybe just Km here.
Would that not change the substrate on the top at all?
It would, but it definitely would. But the difference is on the top, the substrate is multiplied by the other things. Here it's just an addition. And so what that means is if this number is small relative to this number, it's almost like that substrate concentration doesn't matter in the denominator anymore. And so at low substrate concentrations, we expect basically first order in substrate, meaning as you increase substrate concentration, you ought to see basically a linear increase in rate. But at a certain point, when substrate concentration is large, and by that we mean maybe greater than Km, in that case, the rate law simplifies, and we've done some of this before in our steady state approximations for various other mechanisms that didn't involve enzymes, but then the rate law would simplify to this, where you just have substrate concentration in the denominator because it's much greater than Km. Then that substrate concentration would cancel out, and you're left with just Kcat times the enzyme concentration. And that's what this represents is saturation, that is zero order dependence on substrate concentration. And this makes sense if you have enough substrate here that you've bound up all the enzyme. Adding more substrate doesn't get you anything, right? Because you've already taken up all of the enzyme that you can. The only way you can bind the enzyme again is if you free up the enzyme by converting to product. And so if you were to plot rate, if you were to measure initial rates over a time interval where substrate concentration stayed constant, so we'll just do initial rate versus substrate concentration, you'd see linear dependence at first, and then it would plateau off. And this is the saturation regime. Now, sometimes people will formulate the Michaelis-Menten equation a little bit differently. Sometimes they will call this Kcat times enzyme concentration. They'll call that Vmax. That's the maximum speed the reaction can go at when all of the enzyme is bound up, and it's this level right here. Okay, so for example, years ago, when the Michaelis lab first started to do peptide-based catalysts, bifunctional catalysts, they were interested in seeing whether there was Michaelis-Menten type behavior in terms of the rate and substrate concentration and whether they saw saturation or not. And they made some progress at first, but I believe, if I remember the story right, there was some concern about the kinetic assay and whether it was actually giving us information on initial rates. And so I think I was helping at that point with some of the NMR experiments, but in any case, I think as to whether or not you saw saturation type behavior, that was still an open question. All right, so we're going to talk a little bit about an example of this kind of catalysis, and then we're going to talk about how enzymes might evolve, strategies that enzymes might take as a course of evolution for improving catalysis. So a classic example of, well, there are many examples of enzymes that follow this pattern, but one of them is kind of interesting. It's Ricin A. You ever heard of Ricin? No? What is it, Josh? Don't remember? You've heard of it. It's a poison. I believe it's isolated from some kind of bean. Oh, yeah, from the seeds of the castor plant. And it was used, it's an enzyme, it's a ribonuclease. It hydrolyzes ribonucleotides, gets rid of the purine specific adenosine bases, and thereby inhibits DNA and RNA synthesis. And the Soviets used to use it during the Cold War, the KGB used to use it as poison because it's basically undetectable. There is no tox screen that would detect ricin. It's just a protein, and you don't need it in very large amounts to make this happen. So what has to happen for ricin to work? What is the substrate? Well, the substrate is this ribonucleotide, and here you've got the 5' phosphate group, which we're not drawing, and then here you've got the purine base of adenosine. So don't worry about memorizing the structure of this. At some point, maybe if you take Savage's chemical biology class, you'll have to memorize the structure of the 4 bases. You'll have to know the difference between T and U, but for right now, we'll just go there. Now the enzyme, what does the enzyme do? Well, you've got multiple side chains in the active site. You have a positively charged arginine, which looks like this.
On that structure,
Yeah.
is this, I guess the ring that's most to the right, is that a 5-member?
That's a 6-membered ring that's drawn very poorly, so let me take another crack at it. Nitrogen. The problem was that nitrogen needed to be.
Yeah, I think that was.
Okay. I think I've
Is that
got.
how hydrogen
Now I'm really, really sad and embarrassed. Okay, let's figure this out. There we go.
that makes sense.
You're not going to tell the other professors what a moron I am, are you? Okay. Imposter syndrome. It still happens to you when you are a professor. So what happens is there's a water molecule held in the active site, and there's glutamate, carboxylic acid. The first step in the reaction is, so this would be, now I'm showing you in the active site, this would be the enzyme substrate complex, all right? Binding of the nucleotide. Now the rate determining step for the transition state is leaving of formation of an oxocarbenium ion, and the adenine leaves. The adenine base leaves. And one of the roles of that negatively charged glutamic acid side chain is probably to ion pair with the positively charged oxocarbenium ion. And really, it's probably the presence of this residue that helps stabilize this part of the rate determining transition state. As the adenine leaves, then there's going to be a buildup of positive charge on this carbon and on the adjacent oxygen. And then what happens to the adenine base as it leaves? Well, that part is controversial. Probably if you think about the pKa's of the nitrogens that are involved versus the pKa of the arginine side chain, probably the adenine stays as a negatively charged conjugate base. And ultimately it gets, there's a tautomerization process that ends up putting the proton there. But for now, let's not worry about that. Likely there's just an ion pair between that arginine and the adenine. So that's another way that we stabilize the transition state of having that adenine group leave, is as we build up negative charge on the leaving group, you've got a positive charge here to pair with it. As we build up positive charge on the ribose ring, we have a negative charge to pair with it. So that's an example of how an enzyme stabilizes the transition state, and this is the rate determining step. Probably in a fast step after that, you have concerted, and I'm not sure what the slow step is or not, but you have concerted general base type catalysis of that glutamate side chain, removing the proton from water, and then water attacking there, and the products that ultimately leave the enzyme are two different products now. You have the ribose ring, which is now doesn't have the base attached to it. And then you have, I'm trying to see what they show as the product. Yeah. And then that particular isomer of the adenine base. So this is an example of an enzyme that binds the transition state better than it binds the starting materials or the products, and that's kind of what you want if you want catalysis to work. And it's this is just one example of how complicated the situation is. You have to have lots of different groups in the same location, and there are tons of different enzymatic reactions. And if you took a biochemistry course, you'd spend a lot of time thinking about what those side chains were, and you'd learn about the experiments that help you determine which side chains are doing what in the transition state. let's talk, any other questions or issues you want to talk about there? So let's talk about how an enzyme improves. And I'm going to copy down the Michaelis-Menten equation again. All right. And maybe we'll copy down this Km equals K minus 1 plus K cat over K1, and maybe we'll remember that Kd equals K minus 1 over K1. Okay, so how an enzyme improves depends on the relationship between substrate concentration and the existing Km of the enzyme. Okay, and remember, Km sort of contains how well the enzyme binds the starting material and how good catalysis is. So, So let's imagine we're in a situation where the substrate concentration, say the physiological concentration of glucose or whatever enzyme we want to deal with, is greater than the Km for the enzyme. What would that situation mean? Well, that would mean that if substrate concentration is greater than Km, that probably means that, make sure I don't get this right. Make sure I get this right. If substrate concentration is greater than Km, that probably means that equilibrium is favoring enzyme substrate concentration enzyme substrate complex is probably more stable than enzyme and substrate separated. So how would we draw an energy diagram for the reaction under that situation? Here's energy on this axis. Here's reaction coordinate on the x-axis, or reaction progress. Here is the enzyme and the substrate. Then there's enzyme substrate binding, and when the substrate concentration is much greater than Km, you expect most of the enzyme to be bound. The way we're drawing that is the enzyme substrate complex is lower in energy than the enzyme and substrate are to begin with. And then there's some, oh no. Then there's some transition state. This is the enzyme substrate transition state. Then there would be some enzyme product complex, and then presumably enzyme product dissociation. And you get to start over again. And the activation energy that determines the rate of reaction is the energy difference between the enzyme substrate complex and the transition state. So let's think about how you might improve catalysis. Imagine that you start here, and imagine that you uniformly improve binding to both the substrate and the transition state. And I think we'll shrink that down. We're going to copy this over, and we're going to imagine what that looks like. And we may actually decide that we need a little bit more space on the y-axis. Don't you hate it when I do this and you're like, oh, it would have been nice to know that when we were writing it down in pen. All right, what would it look like to uniformly improve binding to substrate in the transition state? Well, that means that, and I'm going to use blue for this, now the enzyme substrate, let's go down, lower it in energy by, let's say 2 squares. So there's the enzyme substrate complex. If we lower the transition state similarly by 2 squares, let's see what that does to catalysis. And I'm not gonna, we're just gonna show, I think for now, where the transition state is. I don't want to make any assumptions necessarily about where the products are going to show up. So do you see how we have lowered the energy of the transition state and the substrate by similar amounts? Okay. What does that do to activation energy? Activation energy for the improved enzyme is going to be exactly the same as activation energy for the unimproved enzyme, because we lowered those amounts. The activation energy that's relevant, the thing that we're worried about, is the energy difference between transition state and sort of the lowest point. Do you see how those two numbers are basically the same? Go ahead, Josh.
So just verifying, so you're saying that concentration of S is much greater than Km?
That's right.
So like, if we just oversaturated the enzyme, does this thermodynamic necessarily look the same way?
Yeah, I mean, what we're saying is, yes, you can get to this point where S is greater than Km if you oversaturate the enzyme. But this could also describe a situation where the physiological concentration that an enzyme has to deal with the substrate at is much higher than that enzyme's Km.
Okay, so it's not if we're oversaturating, it's just like under normal conditions.
Right. I mean, it's going to be the same both ways.
Okay.
Yeah. But Km is going to be an intrinsic property of an enzyme related to the on and off rate for binding and to the kcat, right? And you can make Km more favorable. You can improve catalysis either by, well, it's complicated because Km represents both binding and catalysis. And so it's not necessarily clear that you want K. If it were Kd, you'd want the Km number to be as low as possible. But Km also reflects catalysis and it's in the numerator. So if it's as low as possible, that could mean that the catalysis isn't any good. So it's not fun, but the Km is complicated. Nevertheless, we're talking about a situation where because of its Km value, the enzyme's already saturated. Okay? So if you were to go in and engineer the enzyme such that you bound the transition state and the starting material uniformly, you're going to get no improvement in catalysis. All right? And if you're in a situation where enhanced catalysis gives you enhanced ability to survive, the changes that did this aren't going to be preserved by evolution because they didn't enhance catalysis at all. That means if you're at a substrate, if your physiological concentration is greater than your Km, it doesn't make a huge amount of sense to try to, for nature to try to bind the substrate more tightly, right? And this is why you will find that for many enzymes, the Km value is equal to or slightly greater than the substrate concentration, whatever that is. So is it possible for nature to bind, say, glucose with a Km that's in the micromolar or nanomolar range? Absolutely. Does nature need to do that? Well, not if the glucose concentration in blood is millimolar, right? See what I'm saying? There wouldn't be any driving force to go beyond that point. Okay, so if you're in this saturation regime, how would you accelerate catalysis? The only way to do it if you're in this saturation regime is, and we're going to need another image, you're going to have to differentially bind the transition state more than the substrate. What's that going to look like? Well, let's copy this again. And I'm going to, let's go ahead and change this arrow to be red. And then we'll use maybe purple for differentially binding the transition state. What's that going to look like? Well, starting material and enzyme substrate complex are the same energy, but the enzyme substrate transition state is now lower in energy because we've bound that transition state more than we bound the starting material. And now, activation energy for the improved enzyme is less than activation energy for the starting enzyme, and so we get accelerated reaction. Okay. So I think we already talked about that before when we first started talking about catalysis, that if you bind the transition state and the starting material to the same extent, you're not going to get a lot of catalysis. And so it makes sense that, yes, you need to bind the transition state better than the starting material. But that's when your substrate concentration is greater than your Km. Let's now look at a situation where substrate concentration is lower than your Km. So now you're not in the saturation regime. You're in the linear regime, linear dependence on substrate concentration. Before we move on, any questions there? Okay. So the new scenario is when substrate concentration is lower than Km. What does our reaction coordinate energy diagram look like then, and how does it differ from what we drew before? Well, remember that Km is somewhat related to the binding constant, and if your substrate concentration is much lower than the Km, what that implies is that you're in a situation where your starting materials, let's put them here, enzyme, substrate, starting materials are more stable, lower in energy than the enzyme substrate complex. Right? Okay, so what is our activation energy here? Notice above, when substrate concentration was greater than Km, activation energy was the difference in energy between enzyme substrate complex and transition state. Here, though, it's actually the energy not between the complex and the transition state, but between the starting material and the transition state. We got a bigger hill to go up if the enzyme substrate complex is higher in energy than the enzyme and the substrate are. Now, do you see that situation we're in? The only difference is instead of going downhill to the enzyme substrate complex, we've gone uphill. All right, so now let's do our two different strategies for messing around with the enzyme and seeing what happens. The first is uniform binding of substrate and transition state. What that would look like is the enzyme substrate complex transition state and the complex itself are stabilized by the same amount. Terrible penmanship, but what are you going to do? All right, so what would that look like? Let's copy this, paste it over, and then let's say we stabilize the enzyme substrate complex by like this amount, and then the transition state by a similar amount. All right, now how does that change our activation energy? Our activation energy is between the lowest spot in our starting materials, which happens to be the unbound enzyme and substrate. Compare the red line and the blue line. What do you see in terms of differences? Blue, what is smaller? Blue is smaller, right? That activation energy for blue is smaller than for red. The reason that's the case is because even though we stabilized both of these points by similar amounts, this wasn't our starting point. The enzyme substrate complex was not our starting point. This was. So it doesn't matter that we've stabilized this guy. The difference in energy between here and here is now lower. So when the substrate concentration is less than Km, you can enhance catalysis by improving binding overall uniformly to a point. And what is that point? Well, if you get to the point where the enzyme substrate complex is equal in energy to the starting material, you get past that, and then you're in the situation that we had up above. So if you have an enzyme and it's in a situation where the substrate concentration is much lower than the Km, one way to deal with that is for the enzyme to try to improve its Km by enhancing binding, and it doesn't need to be too careful about whether it binds the transition state. It's okay if it binds the transition state to a similar amount as it binds the starting material. Of course, if you go with the purple scenario where we differentially bind the transition state, you're also going to get an improvement in catalysis. So what would that look like? Well, we would keep all of this sort of the same, but then we would bind the transition state tighter, and then again our activation energy should be lower for our modified enzyme than it was before. Okay. So two sort of situations that enzymes can be in, and you can see two different strategies for enhancing catalysis. One, differentially binding the transition state that works all the time, and the other, trying to bind both the substrate and the transition state to similar extents, that only works when you're below, when your substrate concentration is below Km. Okay. So a couple other things about Michaelis-Menten catalysis. Sometimes people will use the ratio of Kcat over Km to refer, they will interpret that as something like a specificity constant. And I'm not exactly sure what that means. So I'm going to try to find it. Right, so what would, this would be useful if you were comparing enzymes operating on different substrates. Because remember that Km equals K minus 1 plus Kcat divided by K1. So it includes both binding and catalysis. So let's just see what happens if you put them over each other. I don't know. You can use, I guess for our purposes, and we don't need to push it any further than this, you can use this when comparing catalysis of different substrates, where you want to see both the effects of different binding and different binding of the enzyme to the substrate and different rate of the reaction happening. Okay. Interestingly, the units of kcat over km are going to be in the per molar per second. So it's like a second order rate constant. And you can compare kcat over km for various enzymes to get a sense for their overall efficiency. The fastest rate of catalysis by enzymes is called the diffusion limit. You know how in physics you have the speed of light, which is that's the speed limit. The diffusion limit is how fast molecules can find each other in water. You can't go any faster than that, right? Even if your enzyme could operate faster than that, it doesn't do any good, because then diffusion is your rate limiting step. We're talking about how fast the enzyme and the substrate can find each other. And in water at sort of physiological temperatures, this diffusion limit is about 10 to the 8 or 10 to the 9 per molar per second. So the most perfectest of enzymes will have kcat over km near the diffusion limit. All right, so some examples of sort of nearly perfect enzymes are an enzyme called carbonic anhydrase. We don't really necessarily need to worry about what this does. And then there's another called triose phosphate isomerase. Triose phosphate isomerase is involved in glycolysis, and sometimes we call it TIM. There are a couple of different ways that you could have kcat over km values that are close to the diffusion limit, right? You can either have a very, very high kcat, or you can have a very, very low km. For example, carbonic anhydrase, let me make sure I've got these values. It's written here. For carbonic anhydrase, kcat over km equals 8.3 times 10 to the 7th per molar per second. So that's pretty close to the diffusion limit. Km for carbonic anhydrase is around 0.012 molar, whereas the kcat constant is about 10 to the 5 per second. In contrast, for triose phosphate isomerase, kcat over km equals pretty close to the same number, about 2.4 times 10 to the 8 per molar per second. But how it gets there is different. Kcat is around 10 to the 13, whereas km, hold on, that can't be right at all. We'd have to do the math actually. Km for triose phosphate isomerase equals 2.5 times 10 to the minus 5 molar. So who wants to get out their calculator and figure out what kcat would be if we know km and the ratio? We just need to multiply this number. 2.5 times 2.4 is something like 5 and change. 5 point something times 10 to the third. Okay? So compare those two enzymes. And I don't know what that number is. Am I in the ballpark? Did anybody do it?
Yeah, it's 6. It's almost 6,000 actually.
Okay.
It's 6,000.
Okay. Right. So look at how these different enzymes achieved their perfectness. One of them has a pretty high Km. And if that were a Kd binding constant, 12 millimolar, that is cruddy. If you have a 12 millimolar binding constant, that's if you were to invent a drug that bound some protein and the binding constant was millimolar, people would laugh at you because it would not be useful. The person would have to ingest kilos of this thing in order for it to do anything. But perhaps, and I don't know, we could look up what the substrate for carbonic anhydrase is. But if the substrate concentration is around or a little bit greater than that, there wouldn't be any reason to improve beyond that point. So what does the enzyme do? It focuses on improving kcat, and kcat is 10 to the 5th per second. In contrast, triose phosphate isomerase has a much lower binding constant, perhaps again related to its substrate concentration. Km, not a binding constant, but we're thinking about it sort of like that. Its kcat is much slower, right? Only 6,000 instead of 10,000. So multiple ways to get to this near diffusion limit. And sometimes it's, if you want to understand more about how enzymes do this, it can be useful to know both of these numbers to get a sense for what strategies you might use for making these kinds of things happen. Maybe there's a gospel analogy here, right? There are two different enzymes. They have both achieved the measure of their creation in the sense that they are operating as fast as they possibly can, as efficiently as they possibly can. But if you look at their individual components, they have different talents and abilities, and it takes all kinds. I don't know. Find your own gospel analogy there. I'm not sure. All right. So that takes us through the end of catalysis. And there's a lot more to discuss, but I think you probably have the tools to do what you need to do and to at least get started on understanding things as you go about your research. Our next section is going to be on reactions. So chapters 10 and 11 in the textbook. 10 is about addition and elimination reactions. And then 11 is about, let me make sure I'm getting this right, substitution reactions, isomerizations, rearrangements. So last time I taught this class, we didn't even get to chapter 11. There's way too much. These chapters are like 50 to 70 pages long. So there's way too much to actually get through in the amount of time that we have. We'll focus on selected reactions where the story is interesting, and then we'll leave other stuff for you to learn on your own in the future. Okay, so unlike every sophomore organic chemistry class, we are going to begin with addition and elimination reactions. That's like starting undergrad chemistry with 352 or with the late part of 351. So people will, there's a, just as we had terminology in undergraduate OChem to talk about SN2 versus SN1, E1 versus E2, there is some terminology for addition reactions. So you'll maybe hear people use this terminology, maybe not, but you occasionally will. So AD is for addition, and then there's multiple versions of addition reactions. You can have electrophilic addition, where you add an electrophile to something. You can have nucleophilic addition, where you add a nucleophile to something, or you can have a radical addition where you add a radical to something. And then there's going to be some number that describes the number of molecules in the rate determining step, or the order of the rate law. So as an example, ADE2 would mean bimolecular, that is 2 molecules in the rate determining step, electrophilic addition. And your classic example of bimolecular electrophilic addition would be what you learned about in undergrad chemistry in terms of alkene hydration, right? So in alkene hydration, not sure what I want to tell you. I want to make sure I don't do stupid things and mislead you. The rate determining step is formation of the carbocationic intermediate. So that's your 2 molecules. That's the 2. And this is the electrophile part. And it's an addition reaction because by the time you're done, water adds to the carbocation at the more substituted center, and then in a final step you regenerate your acid, which means this is acid catalyzed alkene hydration. And the acid is involved in the rate determining step, so that means this is general acid catalysis. But notice that the thing that gets added to the molecule is water, but we regenerate our acid. Okay, that should look pretty familiar. That should be like total review, but calling it an ADE2 mechanism might be new to you. And we're going to see, I think, in this chapter that there are some electrophilic addition reactions, particularly to alkynes, that actually there's evidence that they involve 3 molecules in the rate determining step, which is actually kind of wacky and crazy. I think we'll stop there for today. So that begins chapter 10. Just looking ahead, we're not going to have an exam till after Thanksgiving. I will let you know as we get closer to that what chapters it will be on. Also beware that next Tuesday is a Friday, because at BYU is so magical that you can change what day it is.
Tuesday is a Friday?
Tuesday is a Friday.
And Monday is a Monday?
Monday's a Monday and Tuesday's a Friday. You have Wednesday, Thursday, and Friday off. And to make sure we get enough Monday, Wednesday, Friday classes, the university has decided that Tuesday next week is not a Tuesday, but rather a Friday.
So we'll have class.
So we'll have class next Tuesday. Yeah, that was a long, Samantha, thank you. That was a long, convoluted way to say we have class on Tuesday.